All right, let's get right into it. Today, we're going to take a journey to the very heart of reality itself. We're going to explore the fundamental rules that run the whole show, from the biggest things you can imagine all the way down to the smallest.
So let's just ask the big question right up front. What exactly are the core principles that make our universe tick? What's the instruction manual? We're going to start with the giant stage, where everything happens, and then we'll zoom all the way down into the bizarre and wonderful world of the quantum.
So first things first, the fabric of reality itself. And it's not just space, and it's not just time. It's actually this unified thing that scientists call space-time.
Think about it. To describe anything that happens, a star exploding or you just clicking your fingers, you can't just say where it happened. You also have to say when it happened. That combination, the where and the when together, well, that's space-time.
You can think of it like a cosmic GPS. To find anything, you need the three spatial directions we all know, right? Length, width, and height. But the secret sauce, the thing that weaves it all together into a single fabric, is that fourth coordinate, time.
Now here's the crucial bit. Even though they're woven together, space and time are not the same. In space, you can go forwards, backwards, lefts, right, up, down, no problem. But time? Nope. It's a one-way street. It only seems to move forward.
And that leads to this really profound idea about space itself. Since every place and every direction is basically the same as any other, it means there's no center of the universe. And this beautiful symmetry, this idea that the rules are the same everywhere, is actually what gives rise to some of the most fundamental laws in all of physics, like the conservation of momentum.
Okay, so that one-way street for time we just talked about, that is one of the single biggest mysteries in all of physics. We all feel it every moment of our lives. But why? Why does it only flow from the past to the future? This is what's known as the arrow of time.
Seriously, think about it. Why can you remember yesterday, but not tomorrow? Why have you seen an egg break, but you've never seen a broken egg spontaneously leap back together into a perfect shell? What's weird is that for most particles, the laws of physics don't really care which way time flows. But for us, reality clearly has a favorite direction.
While the biggest piece of the puzzle is a concept called the second law of thermodynamics. All it really says is that, over time, the total amount of messiness or disorder, the scientific term is entropy, always goes up. And the reason is simple. There are just way more ways for things to be messy and disordered than for them to be neat and tidy.
But hang on a second. What about our brains? When you form a memory, you're taking a jumble of sensory information and creating an ordered pattern inside your head. So, are we breaking the law? Are we fighting back against this cosmic tide of disorder?
Well, not quite. And this is the really amazing connection. See, for your brain to create that little speck of order, it has to burn energy. It has to work. And that work releases heat. And heat is just a bunch of jiggling, disordered molecules. It turns out the amount of disorder your brain creates as waste heat is far greater than the tiny bit of order it created as a memory.
So it all lines up perfectly. Our psychological sense of time, the fact that we remember the past, happens because making memories increases the overall disorder of the universe. And that lines up with the universe itself tending toward disorder. And both of those line up with the fact the universe is expanding. It seems we can only exist when all three arrows point in the same direction.
Okay, so we've got our cosmic stage set. Now it's time to meet the real puppet masters, the forces pulling all the strings. And to do that, we need to shrink ourselves down and dive into the truly strange world of quantum physics.
The word quantum might sound complicated, but the core idea is pretty simple. It just means that at the tiniest scales, the universe isn't smooth. It's chunky. Energy doesn't come in a continuous flow. It comes in little, indivisible packets called quanta. A particle of light, for example, a photon, is one of these little packets.
Now, just to give you a sense of the absolutely insane scales we're talking about with these forces, look at this number. That is a 1 with 40 zeros after it. That is how many times weaker gravity is than the strongest force in the universe. It's a difference that's almost impossible to even wrap your head around.
So you have the heavyweight champion, the strong nuclear force. It's like cosmic superglue holding the centers of atoms together. But it only works over unbelievably tiny distances. Then you have electromagnetism, the weak nuclear force that handles radioactive decay, and then, all the way at the bottom, you've got gravity. Incredibly, unbelievably weak, but with one key advantage. Its range is infinite. So here's the big takeaway. The universe is really a tale of two different domains. Down at the subatomic level, the incredible strength of the strong force is the absolute king. But because its reach is so tiny, once you get to the scale of planets and stars and galaxies, it's gravity's long, patient, infinite reach that takes over and shapes the entire cosmos.
We've looked at the stage and the actors, but now we come to the final and maybe the most profound rule of them all. And this one isn't about what exists, it's about what we are fundamentally allowed to know.
This is the famous Heisenberg uncertainty principle, and it is absolutely critical to understand that this is not a limitation of our technology. We can't just build a better measuring device to get around it. It is a permanent, hard-coded feature of reality itself.
So why does this limit exist? Well, imagine trying to measure an electron. You have to see it, which means you have to bounce a particle of light off of it. If you use a really gentle, low-energy light particle, you won't affect its speed much, but your measurement of its position will be really blurry. Okay, so you use a high-energy, precise particle of light to nail down its position. Great. But in doing so, you've just blasted the electron, changing its speed completely. You just can't win.
You know, a really good analogy is to think of it like the resolution on your TV. No matter how good the screen is, you can't see details that are smaller than a single pixel. It's almost like nature itself has a fundamental pixel limit. There's a built-in fuzziness to reality that you can never get past.
And the implications of this one idea are just mind-blowing. It means nothing in the universe is ever perfectly still. It means empty space isn't really empty. It's fizzing with energy. But the biggest thing is this. It means the universe is not a predictable clockwork machine. At its very core, reality is governed by probability and pure chance.
And this isn't just some weird rule for tiny particles. It is a universal law. This fundamental uncertainty is woven right into the fabric of space-time, and it's very likely a necessary ingredient for any universe to be stable enough to exist in the first place.
So we end up back where we started, but with a completely new view. We've gone from this idea of a predictable, deterministic stage to a reality that's literally built on a foundation of probability. It means the future isn't written in stone. Which leaves us with a final thought to chew on. If the universe is ultimately built on chance, what incredible possibilities are still waiting to happen?